I guess circling back on the Elevate project, I skipped one thing that I wanted to dive in as well. So you got it on your background here, and the legs stand out as something that not an obvious solution that you guys came to for how those walking legs were. Can you design anything stand out in that process, or things that you learned, or how you came up with the design there?
Oh yeah, this was a very long process, a lot of thinking. We we had a goal to still drive with a good quality driving dynamic and be able to walk. And that was the challenge, was what formation of these legs are going to still allow this thing to be a car, like drive like a car. Well, if you look at a car, like, you got wheels at the corners and they're tucked in these fenders. So we started ideating, like, what do we do with the legs? Where do the legs go? Because you could design a vehicle that if the primary goal was just to walk, you could focus all your effort on just walking, and rolling its tires might be something it just does every now and then.
Like a
And
Boston Dynamics dog with tires at the
which is
bottom or
tires,
something.
right? But that thing is made to walk.
Yeah.
And yet, our goal was to make sure that this could actually still just drive on a highway like any car. So that was our challenge. And to do that, we knew we had to fold the legs up somehow when they weren't being used. So that became the challenge, is how do you fold these legs up and have a tire, and where do the legs go? And how many joints do we need? So we went through this whole degree of freedom analysis. What kind of motions can you get out of 3 degrees of freedom? Well, go back to animals, go back to biomimicry. So we actually had a consultant come in from University of Michigan's robotics laboratory. And we had a lot of just sessions with him talking about how he has developed multiple robots at the university and the biomimicry strategies. So we talked about, okay, 3 degrees of freedom gives you an inchworm. You could have a vehicle that could, like, scissor a 3-joint architecture and inch forward. And we said, well, okay, we have a use case where we just need to get out of a ditch. Does that satisfy that? Okay, maybe we could. So we'd ideate, we'd sketch on that. And then we went through, well, what does 4 degrees get you? Okay, now you can have abduction, and you can maybe crab sideways. And then we went to 5. But then we still were struggling that we couldn't steer. So if you couldn't steer, then you start to get like 4-way, like a tank does. Okay, so you could move and you can technically steer by just rolling the left side tires one way and the right side tires back the other way. But if you actually then want to steer while you're going high speed, you get a ton of scrub. And if you get all that scrub, you're just gonna just burn through tires, and you're gonna like have friction resistance. So we said we've got to have a steering joint. So through the whole process, it led us to 6 degrees of freedom, and we figured out a way to tuck it in. And it was actually a sketch I did looking at grasshoppers. And a grasshopper, when they tuck their leg in, their hip and their ankle actually almost come into contact, and they have this giant, thigh and shin joint. It's like if you sat down on your knees and your feet are under your butt. Your ankle is directly in line with your hip joint. And so we said, okay, let's fold them up that way. So we went through that process. We started folding them that way, and then we said, okay, other robots or other quadrupeds on the market are either mammalian or reptilian, and we had to study what that meant. So a mammal, and that's what Boston Dynamics Spot Dog is. Their Spot Dog walks like a mammal, and what that means is that your most efficient walking motion is forward. Okay, that's why cheetahs and horses are just amazing at just running fast and efficient. And your hip joint only has a lateral stability joint. So your primary hip joint axis is horizontal. And you can step sideways real quick, but your main joint is to run forward, and you see that hip joint moving forward. Now, if you think about reptiles or spiders, their hip number 1 axis is flipped, and it's vertical. So an alligator, when it walks, its legs are straight out, and it's actually rotating with their hip pointed, for their first axis pointed up.
Huh.
And so is a spider. Spiders, all six of their legs or insects have six, spiders have eight. They're moving with a vertical hip joint, and that's why I have this amazing omnidirectional movement. The problem is it's not efficient. So they can't do it for a long distance because the weight of their legs is always out from the center of their body. So alligators can do like a crazy sprint, out of the water and grab a gazelle and pull it back in. But an alligator, can't run the Kentucky Derby like a mammal can. So we had this like decision of which one do we go for, or could we do both? And what we think is really novel about our design is it's the first one that actually did both. And it's by spinning the hip axis and tucking the legs up, we can do a primary mammalian motion, but we can swing the leg out and actually go into a reptilian position. Because of the 6 degrees, you can turn your tires and you can use your feet and you can walk in both directions. So if you were to go online and watch some of the videos from CES of our robot, we built 2 functional prototypes of this. And we can move it in and out of mammalian versus reptilian. So that was